Section 4.2 Integer Representations and Algorithms. So we can represent an integer in a lot of ways. Let b be an integer if b and b is greater than 1. If n is a positive integer, they can be expressed uniquely in the form n equal a sub k b to the k all the way down to a sub 1 b to the 1 plus a sub 0. Where k is a non-negative integer, a0 through ak are non-negative integers less than b, and a sub k is not equal to 0. This representation is called the base b expansion of n, denoted as follows there in part 2. Now this definition can be hard to follow, but the thing you want to lock onto is that expansion right there, that a sub k b to the k part. So let's go through some examples showing you that this theorem holds true. So to begin with, you're actually very familiar with this idea. In fact, when you were a kid, we taught you the number 534, and this is how you thought of it, right? There were 5 100s, 3 10s, and 4 1s. And you can see it following the expansion there, right? 5, 3, and 4 are all integers less than base 10. And then the increments there, right? 10 squared, 10 to the first, 10 to the 0. So this 534 represented 5 100s, 3 10s, and 4 1s. And so if we see something like 642 base 8, what we're saying here is 6 8 squareds, 4 8s to the first, and 2 singles. So this is the number that we're used to in base 10, 418. So these are if you wanted to represent 418 in base 8, it would be the number 642. You're probably most familiar, or most of you are familiar with this in terms of binary. So the binary expansion or representation of 10100011 in base 2, we expand it out as follows, and we get that it's the equivalent to the number 163. We also have hexadecimal digits, right? In this case, we run out of regular representation, so we need 16 unique symbols for our integers. So we need something for 10, 11, 12, and we don't want to use 10, right? That would be the integer after 9. So instead we use a, and we don't use a 10 because that would make the representation really hard to read. So when we see a, b, 5, 6, what are we trying to say? Well, we have a, that's 10 copies of 16 cubed. We have b, which is 11 copies of 16 squared. We have 5 copies of 16, and we have 6 ones. Add all that up. This is 43,862. One thing to note here is that the choice of base affects how long the representation is. So note that 43,862 in our regular base 10 representation system takes 5 digits to represent. Base 16 has more symbols to choose from, and it can actually represent a number that large with only 4 symbols. This is pushed to the extreme in binary, where to represent a number for us that's as short as 3 digits, 163, 163, takes 8 digits. So here's an algorithm for doing the base expansion to convert the base from one form to the other. So for example, say we have 1,542 in base 10. That's the easiest way to see what's going to happen here, because well, let's just dive into the example and I'll show you how this algorithm is working under the hood. So the first thing it's going to do is take that 1,542 and divide it by 10. So at this stage, what's happening is we're saying, okay, the basic building block that I have are 10s. So we go through and we say the 1,540 can be constructed out of 10s. What can't be constructed out of 10s? That remaining 2. So now in the next step, we're focused on that 154 copies of 10. We're saying, can those be represented with larger building blocks? So we take that 154 and we divide by 10 again. You'll note that what this is doing, since we've now divided by 10 twice, we're asking, can 100 go into this? Sure enough, it can 15 times with a remainder of 4. We repeat. 10 goes into 15 just once with a remainder of 5. Bring the 1 down. 10 goes into there 0 times, remainder of 1. We now read off those remainders, and we get that this is the number 1,542. Note we didn't change anything here because it was a base 10 conversion, as it were. So let's see this with another example. Let's find the octal expansion of 12,321. So we're just going to keep repeatedly dividing by 8. So we divide by 8 the first time, remainder of 1. Take that 1,540, bring it down, divide by 8 again. You get 192, remainder of 4. Bring the 192 down, divide by 8. Remainder 0. Bring the 24 down, divide by 8. You get a 0. Bring the 3 down, divide by 8. It can go in there 0 times, remainder of 3. So we get the octal expansion 30041. What about the hexadecimal expansion of this number? Well, hexadecimal has base 16, so we divide by 16 repeatedly. This process is actually going to be really important to us. It's a very clever way to get these base expansions. So in hexadecimal, 12321, 12,321 can be written as 3021 in base 16 in hexadecimal. Okay, well, let's try the binary expansion of 12,321. And this takes a very, very, very long time, right? The base, because we're dividing by 2, it just keeps dividing by 2 and keeps dividing by 2. So this can be a lengthy process, but it's still pretty clever. So we get a representative form in base 2, 1 1 0 0 0 0 0 0 1 0 0 0 0 1. It's almost so long it's not worth me reading aloud to you. Do try and copy, right? Sit down, really look at this, the algorithm, the way that it's working, because we'll be using this in later chapters and kind of reversing and expanding upon this idea. The other way to do it is just to have a table, right? So if you want to represent this binary number in octal, well, since I'm looking at octal, I think the real trick to using a table is making sure that you don't look at parts of the table that aren't relative or aren't related to what you're looking at. So in this case, we're looking at the octal expansion. So in an octal expansion, you only have 8 digits to choose from. So that would be 0 through 7. So I do not need to consider the rest of the table for this. You'll note that that means that any octal digit, 0 through 7, can be represented with 3 binary digits. So I'm going to rearrange the binary I have here. Note they're in increments of 4, which is pretty standard, but I want them in increments of 3, because for each 3 digits in binary, I can represent them with 1 digit in octal. So I get 1, 2, 2, 6 in octal. 1, 1, 0 is the same as a 6 in octal. 1, 0, 1 is the same as 2 in octal. Now the trick there is that you look up the table, and in binary you don't see a 0, 1, 0, but you pad to the left with the representative number of zeros. Let's try the hex expansion. So as I'm in hex, that means I need all the way 0 through 15, so I need the full table now. You'll know that this means that every cluster of 4 binary digits will convert to 1 digit in hexadecimal. So I don't need to change the groupings any. I do need to pad with zeros on the left there to find 1 0 in binary is the same as 0 0 1 0 in hex. So in hex, I end up with 296. What about the binary expansion of 742 in octal? and I want to come up with a binary expansion for it. Well, again, I don't need anything past 7 because there is no digit greater than 7 in an octal base. So for each one of these, I just grab the binary representation below it, again, padding with zeros if necessary. Let's find the binary expansion of 7CE2 in base 16. I need the full table for this. Each one of those goes into each hexadecimal digit there will go to 4 binary digits. So I get the following expansion. So in this chapter and the last chapter, right, to do this binary expansion, that sort of thing, we've been doing a lot of division and moduloing. So we need a fast way to do this. We need an effective algorithm for doing this. How does your computer do division and modular arithmetic? So given the A and the D and Z, can you calculate A divide D, and can you calculate A mod D? For example, how would you actually find 19 divide 4 and 19 mod 4? Think about it for just a second how you would actually do this. And one of the first things that comes to mind is what we're going to call brute force, right? I just start subtracting 4 until I can't take away 4s anymore. In fact, I can't recall off the top of my head, but I believe in either this in 4.2 or 4.1, I've said exactly that when I was talking about modular. I said, oh, well, how many, I can take away 2 rotations of the clock, right? How many times can I take away 4 from 19? In this case, I was able to do it 4 times. So 19 divided by 4 was 4. The remainder was 3, so 19 mod 4 is 3. So here's an algorithm to do just that. You notice the main thrust of it is in that while loop part. How many times can you subtract it? There's a big section here at the bottom that has to deal with, well, what happens with negative numbers? Because if you'll recall, we had to make sure the remainder was positive. So right up there at the top of the code, we start by assigning R to the absolute value of A. So let's see this in action. Let's say I want to find negative 19 divide by 4 and negative 19 mod 4. So we start with the assignment there at the beginning. Q will be assigned to 0. R will be assigned a absolute value of negative 19, so a 19 at the start of the loop. The while loop runs. It will run 4 times, giving me a Q of 4, a remainder of 3 at the end of that while loop. Now the if statement triggers, right, because our A was less than 0, assigning R equal to D minus R, which is a positive 1, and then because of that, we crank one more minus 4 to set it right. We did run through the loop. We subtracted 4 4 times. Well, to do this now, we need to subtract 4 5 times. So negative 19 divided by 4 is negative 5. And the remainder of negative 19 when you divide by 4 is 1. Note that this goes all the way back. This is how we would write it using the division algorithm. Negative 19 is equal to 4 times the negative 5 plus 1. The remainder has to be positive. So one thing we're going to start laying the groundwork now. One thing we're going to start laying the groundwork for making a problem that we can solve easily that the computer can't, given that we know a secret piece of information. So the modular exponentiation here, we want to compute b to the n mod m efficiently. So we want to be able to do this quick. So we let n be the base 2 expansion. So this n is represented in binary. Then b to the n, right? We think of that b to the n as being b raised to the binary base expanded form of that number, right? The algorithm we started this section with. Typo. right? Using our exponent rules, these are multiplications. I apologize. Right? Additions up here, and the exponent become multiplications down here. Sorry about that. So let's say we want to compute 3 to the 11th power mod 5. We're going to need a couple pieces. The first is we're going to take a look at that binary expansion. Oh no, it was typed wrong there. Recall that this should be multiplications right here. So 3 to the 11th power, we're going to convert that 11 into a binary representation. 11 in binary is 1011. Next, we use our base expansion that we saw at the beginning here. So what we were after really is representing 3 to the 11 as 3 to the 8 times 3 squared times 3 to the first. Note that when represented here in the final form, you can see that this is, we went through all this work, but now you can see that the exponents would add together. 8 plus 2 plus 1 is 11. But the way we chose them are very important. We'll see why in a second, why we needed it to be base 2. So the next part of this process is we're going to calculate 3 squared, 3 to the 4th, 3 to the 8th, all in a modulo 5 world. And again, hold on, you're going to see all this come together near the end. We did this in the last section. What we're trying to leverage is that part there underlined in the blue and the green. So keeping that little fact in mind, we're going to take, sorry, the part underneath the underlined sections, we need the multiplication rule. I'm going to tuck that up here in the top because we're going to be using that in just a moment. So 3 to the first mod 5, well, that's pretty simple. 5 does not go into 3, remainder 3. 3 squared mod 5. Well, now we can start to use the rule from above. And it's not going to gain us a lot this time, but 3 squared mod 5 can be rewritten as 3 mod 5 times 3 mod 5 mod 5. Using our rule again highlighted up there above. So this gives me 9. 9 mod 5 is 4. 3 to the 4th. Now we start to be able to leverage the advantage here. I rewrite 3 to the 4th mod 5 as 3 squared mod 5, which I've already determined in the previous step to be 4. So I can immediately rewrite 3 squared mod 5, replace that with a 4. 3 squared mod 5, replace that with a 4. So instead of looking 3 to the 4th mod 5, I'm looking at 16 mod 5. So you may be thinking, well, I can still do 3 to the 4th in my head, but now we go to do 3 to the 8th. And I don't want to have to calculate 3 to the 8th. And I don't really need to here, because I know that individually 3 to the 4 mod 5 is just 1. So instead of calculating 3 to the 8th mod 5, I can just do 1 times 1, mod that result by 5. So it's way easier to see that that will just be 1. So I have the results that I need. 3 to the first mod 5, 3 is 3. 3 squared mod 5 is 4. 3 to the 4th mod 5 is 1. 3 to the 8th mod 5 is 1. So start again with that 3 to the 1st mod 5 equal 3. Recall, 3 to the 11th is 3 to the 8th times 3 squared times 3 to the 1st. All of this was to calculate 3 to the 11th modulo 5. So now when I go to do the second part that I need, 3 squared times 3 to the 1st, I can now use again rule 2 up there and rewrite this as 3 squared mod 5 times 3 to the 1st mod 5. So I can take the modulo of the individual pieces first, then modulo the result. So this is 4 times 3, 12, mod 5 is 2, right? 12 divided by 5 has remainder 2. Right, I calculated that 3 to the first mod 5 in the previous step, and I have 3 to the second mod 5 from the previous step as well. So I go to calculate 3 to the 8th times 3 squared times 3 to the first. In this case, I'm going to group 3 squared times 3 to the first because I know what the result of 3 squared times 3 to the first mod 5 is. So I'm able to replace the 3 squared 3 to the first, 3 squared times 3 to the first mod 5 with a 2 that I just found out in the previous line. So instead of having to calculate 3 to the 8th times 3 squared times 3, I can just do 1 times 2 mod 5, which is 2. So the result is just 2. Now, the thing I want to focus on here is 3 to the 11th is actually 177,147, right? That is a massive number. So imagine trying to do this with the brute force algorithm, right? You'd have to subtract 5, subtract 5, subtract 5. How many subtractions of 5 would we have to do to get mod 2? The other kind of, so not only would we be here forever, the other kind of fascinating thing that's happened here is that I don't actually know. I don't know how many times 5 goes into that number. All I know is what the remainder would be. So here's the compact form of that code written. We're going to take x, assign it to 1, and we're going to keep incrementing the power up by doing b mod m. So I'm going to go over the trace here, but it's one of those situations where after I do a couple lines, you should sit down and try this out for yourself. So we want to compute 3 to the 171 in a mod 25. So I start binary expansion of 171. I use this to rewrite 3 to the 171 as 3 to the 128 times 3 to the 32nd times 3 to the 8th times 3 squared times 3 to the first. Since this code is a little more complicated than some of the other snippets we've looked at, I'm going to track the power and x at the start, going at the start of each iteration of that for loop, and again at the end. So first, I know how many rows there are going to be, right? This will run from 0 to k minus 1. Looking at my base expansion up there, I can see that 171 is represented by 8 binary digits. So I need 8 rows, 0 through 7. Next, I now know what the a sub I are. Again, because I have the binary expansion in front of me, this part can be tricky. Note that from the code, we have to be given this binary expansion, right? That's part of the input for this procedure. And then a sub 0 is the first digit, and a sub 7 will be the last digit. So whenever you're reading this off, just make sure it kind of goes in reverse order here, right? From you're reading these digits off from the beginning of the number over instead of left to right. It's just a common thing I've seen go wrong before. So start of the first iteration, I assign x to 1, and the power is equal to b mod m. So running at the start of this, x is 1, power is 3. Now the important thing to track as we run through here is whether or not we trigger that if statement. If the a sub I is equal to 1, then we assign x to be x times power mod m. In this case, the a sub I is a 1, right? A sub 0 is 1. So, right, the first binary digit is a 1. So x is assigned to 1 times 3 mod 25, which is a 3. Do our power increment. We're going to do this every time. Take power times power and modulo it. So in this case, we take 3 times 3 mod 25. Well, 3 times 3 is just 9. Modulating by 25 doesn't change that. So when I go into the next iteration, my x and power are at the start of this iteration the same that they were at the end of the last iteration. So do I trigger the if statement? Yes, I do. A sub 1 is equal to 1. So I need to reassign x and, as always, increment the power. So going into the next loop increment at the start of it, x is 2, power is 6. However, this time the a sub I, right, a sub 2 in this case, is 0. So I do not trigger the if statement. I just need to increment the power. 6 times 6 mod 25 is 11. Next iteration, a sub I is 1, so I need to recalculate my x, and I need to increment power. Here, no triggering of the if statement, increment the power. Trigger the if statement and increment the power. Don't trigger the if statement, increment power. Finally, in the last step here, the if statement will trigger, I still increment the power. I end up with the final assignment of x is 22, power is 21. So if you were asked to trace this, you wouldn't necessarily have to use the same table, but I claim that a lot of these calculations here on the right would need to be seen, right? So I have for each row here, you can see what the I is, what the a sub I is, right? Two of the things in each loop. And for at least for this one, since it's a little more complicated, I'm noting what x and power are at the start of the loop, what they are at the end of the loop, and I'm showing any of the calculations that occur within that for statement each time. So at the end of all this, I'm going to return to 22. And yes, I went a little bit faster here, right? You may not have instantly known that 16 times 16 mod 25 was 6. But I still want to take a look at what we've done here. 3 to the 171 is this massive number displayed on the screen right now. Let's shorten it down a little bit. This is 3.87 times 10 to the 81st power. And while yes, I went a little bit faster, you could have done what I just did. I mean, let's stress out and say you did it in 20 minutes. That's still impressive, right? That we were able to do a mod 25 calculation of a number this large by hand. And part of the reason for that is that the largest thing we're ever asked to calculate, right? Because we keep mod by 25ing at the end of every step. We mod 25, we mod 25. So the largest number we're ever having to deal with is 24. So the largest possible calculation is 24 times 24 mod 25. That's as big as the numbers get. To put just how big this number is in perspective, if you rewrite this as 39 times 10 to the 80. 10 to the 80 is roughly the estimated atoms in the visible universe. So we're 39 times that number. That's how big this number was, and we were able to do it relatively by hand here. So the largest thing I asked you to do, again, would have been 24 times 24. Now, we're not going to dive too far into it, but this happens to then work on the order log m squared times log n, log, which broad strokes here means that this operation happens with on big O m, not n, m squared.